To another session of circuits and networks. In today's class 4 under magnetic circuits, or we call as coupled circuits, we'll see some numericals based on dot convention. So here you can see there are three different circuit arrangements where you have dots which are placed in front or back side of inductors. In fact, these inductors are called here as coils. So you can see, for example, 4 henries and 5 henries are the self-inductance values of this particular arrangement, and 1 henry is the mutual inductance between these two coils. So like this, we are going to see different numericals. First, we need to see what we have studied earlier about inductances in series, where you have the coil 1 and coil 2 arrangement under figure 1 and figure 2 as cumulative and differential. In order to understand in a better way, if at all I put a dot convention like this, by assuming coil L1 and coil L2, the current which is flowing into the coil is in the same direction. You can see the dot convention and the direction of the current are in the same direction in both the coils. So this type of arrangement is called as cumulative arrangement. The mutual inductance formed between these two will be M12. So self-inductance of this coil L1, self-inductance of coil of this L2 has mutual relation as M12 or M21. One with comes with L1, one with comes with L2. In that case, when you take M12 or M12 equal to M, I'll be having a general formula of L, that is the total inductance, which is equal to L1 plus L2 plus 2M. Now for differential arrangement, this is how the dot convention is assumed. So here L1, L2 are the two coils having self-inductances, and M12 or M21 is the mutual inductance formed between these two coils. Now here the current direction in coil 1 is in this direction, whereas the same current in series arrangement, it is flowing in opposite way. In this case, the formula of total inductance would be L equal to L1 plus L2 minus 2M. Now inductances in parallel. We have seen from figure 3 and figure 4 from earlier classes. This is the arrangement for cumulative, and this particular figure 4 represents the differential. When you go with the dot convention, this is how the coils are placed, and dot convention is taken in this direction. This is the condition for cumulative, and for this the formula obtained is L equal to L1 L2 minus M square whole divided by L1 plus L2 minus 2M. In our earlier classes, we have seen the actual derivation of inductances in parallel, whether it is arranged in cumulative way or differential way. So please go through that particular video where you're going to understand the proper derivation of total inductance calculations for cumulative as well as differential. Now, when you're going to understand the same concept of differential arrangement, the coils are assumed to be placed like this. In this case, the value of L will be equivalent to L1 L2 minus M square by L1 plus L2 plus 2M. So this is how the dot convention is studied with the flow of direction of current. Let us go with the problem. For the network shown below, we have to calculate total inductance between A and B. So 4 henries, 4 henries and 4 henries are the self-inductance values. The value between these two coils is 2 henries, between these two coils is 1 henry, and between these two coils it is 1 henry. So when we go with the solution, we'll take the help of formula L equal to L1 plus L2 plus or minus 2M. So based upon the direction of the flow of current and dot convention, the formula can be framed like this. So here we have three coils. So the mutual inductance between these two coils can be treated as M12, whose value is here 2 henries. Between 4 and this 4 coil, this coil and this coil, the mutual inductance is assumed to be M23 or M32. Similarly, between these two coils, M31 or M13, whose value is 1 henry. So we are going to take the this formula. L is equal to, first you take the all inductances values, L1 plus L2 plus L3. So L1 plus L2 plus L3 minus, first you see here the dot is coming out from the coil, and here the dot is entering into the coil. So the mutual inductance formed between these two coils will be negative. So individually with coil 1, the mutual inductance is 1. Individually with coil 2, the mutual inductance will be same M. That's why it is here taken value as minus 2M. Why minus? Because both the dots are opposite to each other. That's why minus. So minus M or minus M1 minus M1 results in minus 2 M12. So this is how we got here minus. Then you see between coil 2 and coil 3 how the arrangement of the dot is. In coil 1, sorry, in coil 2, the dot is on this side, whereas in coil 3, the dot is on this side. So these two are quite opposite. And that is why we have taken minus M23 of coil 2 minus M23 of coil 3. So it becomes minus 2M23 or 2M32. So that's why we got here minus. Now when compared to coil 1 and coil 3, here the dot is outside the coil. Here also the dot is outside the coil when you assume the current to flow from A towards B. So in both the cases, the condition matches, and that is why plus M31 for coil 1 plus M31 for coil 3 results in 2 times of M31. So this is how we frame the formula based upon the directions of the dots by assuming the current to flow from A to B. So when you're going to substitute the values, you have L14, L24 and L34 minus 2. This M12 value is here 2 henries minus 2. Here M23 value is 1. So that is why here 1 plus 2 times again the mutual inductance between this coil and this coil, it is 1. So that's why it is 1. So minus 2 and plus 2 they go off, and you have here 4. 4 minus 4 it is 0. So therefore the value is 4 plus 4, that is 8 henries. What if the direction of the dots are changed? So here you see the current is assumed to flow from A to B, and the values of self-inductances are changed, mutual inductances are also changed, and dot conventions are also changed. The current is assumed to flow from A to B, and dot is placed before the coil 1. Here the dot is placed after the coil 2, and here also the dot is placed after the coil 3. By assuming current to flow from A to B, this is the dot conventions they have given, and we are assuming the current to flow from A to B. Now how to frame the total inductance formula. So here total inductance, first you take the self inductance values 4 plus 5 plus 6. So L1 plus L2 plus L3, that value is obtained. Now observe the first two coils, that is 4 henries and 5 henries, mutually between these two the value of inductance, it is 1 henry. So one with respect to 4, one with respect to 5, and both are opposite. That is why minus 2M12. I hope you understood this particular frame of formula. Now you see coil 2, coil 3. Coil 2 has 5 henries, coil 3 has 6 henries, and the mutual between these two values is 2. And both the conventions of the dots based upon the flow of current from A towards B is positive. That's why we are taking 2M23, or you can take one with respect to 5, one with respect to 6 as M23 and M23, and later you can add, then you'll get the resultant as 2M23. And finally the coil 1 and coil 3. In coil 1 the self-inductance value is 4, in coil 3 the self-inductance value is 6, fine. And the mutual inductance which is found between these two, that is 3 henries, is obtained in opposite way, because here the current is assumed to flow from A to B. The entering current and the dot is same for coil 1, which is 4 henries, whereas in coil 3 the current is coming out of from the coil. So that is why the mutual inductance found between these two will be negative. Negative M31 pertaining to coil 3, negative M31 pertaining to coil 1. So overall minus 2 times of M23. Now we just substitute the values. So we have 4 plus 5 plus 6 as 3 self-inductance values. minus 2 times multiplied with M12. M12 value is 1. M23 the value is 2, and M31 the value is 3, taking negative side. So overall you'll get the value of inductance for this network as 11 henries. Sometimes the arrangement is given in this fashion. We have to find out the equivalent inductance for this circuit, where you have coil 1, coil 2, coil 3, whose values are given as 7, 15, 10 respectively. The mutual inductance between these two is 2 henries, between these two is 3 henries, and between the outer two coils, that is coil 1 and coil 3, there is 1 henry. So find out the total inductance. So total inductance will be L1 plus L2 plus L3. So the same value plus. Now you see here the current is assumed to flow from this direction to this direction. So current is flowing in this direction. So here you have dot and you have the direction of the current, both are positive. Here also the dot and the current both are positive. That's why plus M12 plus M12, that is 2 times of M12. That is how we got this formula. Now you see coil 2 and coil 3, the direction of the currents are differential, and that's why mutual value will become negative. So minus M23 minus M23 repeated 2 times. So that is why it is minus 2 M23. And the same case exists for coil 7 Henry as well as 10 Henry, whose mutual value is 1, that 2 minus. So minus 2 M31. Substituting the values of this, L1 as 7, L2 as 15, L3 as 10, and M12 value as 2, M2 value as M23 value as 3, and M31 value as 1. I'm going to get the value of total inductance as 28 henries. Now if the same network is having coil arrangements in different fashion, that is here it is entering, for coil 2 it is leaving, again for coil 3 it is entering, self-inductance values 14, 12, 8 are given. Now if K1, which is known as coefficient of coupling, value is given as 0.2 between coil 1 and coil 2, K2 between coil 2 and 3, coefficient of coupling is value given as 0.3, and or between coil 1 and coil 3, the coefficient of coupling value is given as K3 equal to 0.5. Now find out the total equivalent inductance. So for this, because we have K1 which is placed between L1 and L2, there is 14 henries and 12 henries. So M12 or M21 will be equivalent to K1 times L1 L2. This formula is being derived from our previous classes. The relationship between mutual inductance and self inductance in terms of coefficient of coupling. The formula is given by K equal to M by under root L1 L2. So from the standard formula, this formula is framed. Now just substitute the values of the given parameters, that is K1 is 0.2, L1 is 14, L2 is 12. With this we'll get the value of M12 or M21, whose value is nothing but 2.59 henries. Similarly, M23 would be equivalent to 2.93 henries, and M31 or M13 will be equivalent to 5.29 henries. Now employ the same formula that we have framed based upon the dot convention. So here total L is equal to sum of these three inductances, self inductances, that is 14 plus 12 plus 8, and you can see between coil 1 and coil 2 the mutual value, because of the value of K1, the mutual it is opposite, so that is why it is minus 2 times of 2.59 what we have derived from M12. Check out the dot convention between coil 2 and coil 3, that is also opposite, that is why here we have the value as minus, and repeated mutual inductance due to coil 2 and coil 3 repeated twice, so that is why 2 is over here, minus is the same, this is the convention based upon the dot, that is opposite, that is why we have here minus, and 2.93 just we have calculated from this formula. Finally, between coil 1 and coil 3 the mutual parameter is positive, so that's why it is positive, and the value we have obtained for M31 or M13, it is obtained to be 5.29. So overall, if at all you substitute the values, you're going to get 33.54 henries. So this is how you solve torque convention problems, especially for the series circuits. Now in the third question you have two coils having self-inductances of 3 millihenries and 5 millihenries respectively are connected in parallel. If the mutual inductance between them is 2 millihenries, find the equivalent inductance. Now for a parallel circuit with the given parameters of L1, L2 and M, for cumulative coupling, this is the formula, that is L is equal to L1 L2 minus M square by L1 plus L2 minus 2M. So if we assume that the uh, arrangement of the parallel circuit is cumulative, then the formula for total inductance would be, taking these values, 3, 5 minus M value is 2 milli, so 2 to the power of 2 whole divided by 3 plus 5 minus 2 times of 2. So here all the values of the inductances, that is self and mutual, are given in milli. That's why I have taken 10 to the power of minus 3 outside. And finally, when I'm going to calculate the values, I'm going to get 2.75 millihenries. Is this clear? Right. For differential arrangement, the above formula changes to this. The denominator will be having plus 2m, and substituting the values of L1, L2 and M, we'll get the value as 0.91 millihenries. So this is one way of solving the parallel circuit problem consisting of self-inductances and mutual inductance. What if the circuit is given like this: coil A and coil B with the mutual inductance values? You can see self value of this is 4 henries, self value of this coil is 5 henries, that is coil A and coil B, and the mutual between these two is 2 henries. You can see the torque conventions are in opposite direction, and we are assuming that current is flowing from top to bottom. The current is flowing from top to bottom, whether it is in coil A or it is in coil B. We are assuming that the current is flowing from top to bottom. Then based upon that, the torque convention, how the output is obtained, let us see. First, let me calculate coil A self inductance. In fact, the total inductance of coil A, that will be nothing but L1 minus M12. L1 is what? L1 is the self inductance value minus M12. What is minus M12? M12, there is in opposite direction. That is why I am taking here the value of the inductance as minus M12. Similarly, for coil B also, I'll take the value of L2 minus M12. M12 or M21, you take the mutual value to be the same. So overall for this coil B, the value will be 3 henries. So coil A we get 2 henries, coil B will get 3 henries. Now based upon the standard inductor arrangement in parallel, we'll get 1 by L is equal to 1 by LA plus 1 by LB. So this is another way of estimating the parallel arrangement problem, whose value will be equivalent to 6 by 5 or 1.2 henries. So this is also another way to solve the problem. I hope you understood how we have framed this formula based upon the given coil arrangement. In another problem, two inductances are connected in parallel. Their equivalent inductance when the mutual inductance aids the self inductance is 8 millihenries, and it is 4 millihenries when the mutual inductance opposes the self inductance. If the ratio of self inductances is 1.4 and the mutual inductance between the coils is 3 millihenries, find self inductances. So here we have to find out what is L1 and what is L2. Based upon the aiding and opposition, the cumulative and differential arrangements are framed. So first take the data, that is uh, cumulative value is given as 8 millihenries, differential arrangement value is given as 4 millihenries, and mutual inductance between these two coils is given as 3 millihenries. Also the ratio of self inductances, that is L1 by L2, here we are assuming to be as 1.4. So if at all we assume L2 by L1 as 1.4, the values of L1 L2 will change, that's it. So if L1 to L2 ratio we are taking as 1.4, then what is the answer we are going to get? We see. So we know that for cumulative coupling, this is the standard formula, and L cumulative value is given as 8 millihenries. So I'll substitute here 8 equal to L1 L2 minus mutual value is 3. So that is why minus 3 square whole divided by L1 plus L2 minus 2 times of 3. This we are framing as equation 1. Also, from differential arrangement, the formula is L equal to L1 L2 minus m square by L1 plus L2 plus 2m. And the value of differential inductance is obtained to be, or it is given as 4 millihenries. To substitute the values. So I'm framing equation 1 and equation 2. So from equating these two equations, because on the top L1 L2 minus 3 square for equation 1 and L1 L2 minus 3 square for equation 2, they both values are equal on the numerator, so I can equate the denominator values. So with this I'm going to get L1 plus L2 equal to 18. Let me take this equation as 3, and also given data that L1 by L2 is equal to 1.4. This implies L1 equal to 1.4 L2. If at all you take L2 by L1 equal to 1.4, the equation changes. So keep that in mind. Here I am assuming L1 by L2 equal to 1.4. So L1 will be equal to 1.4 L2. I'll take this equation as 4 and I'll substitute in equation 3. So I'm going to get the value of L2 as 7.5 millihenries. Once L2 is obtained, L1 is obtained from equation 4, which is equal to 1.4 into 7.5. So the value will be equal to 10.5 millihenries. So this is how different problems are solved with the help of dot convention technique as well as series and parallel arrangements. So I hope you like this class. Please share among your friends, subscribe to this channel, and please press the bell icon for future notifications.